So the question is, why is it that I squared is -1? Why should that be true? First of all, this is a definition. Somewhere, sometimes, some people decided that we're going to define I squared to be -1. So if someone asks, how come I squared is -1? The answer, well, because we defined it so, is not very satisfying. So I'd like to show you another reasoning why we decided to define I squared to be -1. All right, let's get started. First, we should discuss the idea of the expansion principle. The expansion principle guides our decisions when we are introducing new definitions into our mathematical system. One example would be for this is that we started with the natural numbers, then we developed or discovered, that could be debated, which one, the negative numbers, and then fractions. Whenever we step out from our world to a larger world, we refuse new definitions if they would conflict with something we already have. Let's see an example. In lower level algebra, some of my students want to add fractions like this. Well, why not? It's so much simpler, right? Add the numerator, add the denominator. Nice, easy to remember, symmetrical. Why wouldn't we define addition of fractions that way? Well, one reason we didn't do that was the expansion principle. Because if we were to define fraction addition in such a way, then we would make statements that are already true, all of a sudden we would make them false. Right? We already have this statement that 2 plus 3 is 5. But with our new definition, if we thought of 2 and 3 as 2 over 1 and 3 over 1, all of a sudden we would have two different answers for the same question. That is not allowed. Because of this, there was no way that we would define fraction addition like this. All right, let's see another example for the expansion principle. We defined exponentiation as repeated multiplication. That definition is only meaningful for positive integer exponents. And then, of course, we wanted to define negative exponent. Say we would like to define a to the -2. We ended up defining it as 1 over a squared. So if someone asks, oh, why is a to the -2 the same as 1 over a squared? The answer is, well, that's a definition. This is how we defined it. But then the next question, the next logical question is, okay, why did you define it? This is what we could call a theorem. If we want to define a to the -2 and we want to preserve the statement a to the n over a to the m is a to the n minus m, then a to the -2 can only be 1 over a squared. Even that may not work. So this is just a necessary condition. And the computation is quite simple. We recognize -2 as 1 minus 3, and then we apply this rule, well, kind of backwards, right, from right to left, and we rewrite a to the 1 minus 3 as the division between a to the 1 and a to the third power. And after cancellation, we get 1 over a squared. Here is where this rule is acting, right here. Any other definition would mean that we would ultimately lose this rule. By the time we were eager to define negative exponents, we got used to this rule. Turns out we kind of like it. So let us see how the expansion principle required that we define I squared to be -1 within the complex numbers. So here is the claim. If we extend our world from the real numbers to the complex numbers, and we want the absolute value of z1 times the absolute value of z2 to be the same as the absolute value of z1 times z2, then I squared equals -1 is our only option. Maybe even that doesn't work. That is the thing that we can prove. And then after this proof, naturally, we defined I squared to be -1. So let's see how we can prove this statement here. We are not going to build up the complex numbers from scratch, because right now I'm assuming you know a little bit about complex numbers. So as you may know, complex numbers are defined as a pair of real numbers with some strange rules. Z, generally a complex number, is the same as a plus b times I, where a and b are real numbers. There is a one-to-one correspondence between the point ab and the complex number a plus bi. The absolute value of a real number is its distance from 0 on the number line. If you cross out real and line and enter complex and plane, you get the definition of the absolute value of a complex number. So it is again a distance, therefore a non-negative real number. And you can also see that this definition does not harm the old one. The absolute value of a complex number can be found by the Pythagorean theorem. Next to what we did, we defined addition, subtraction, and multiplication by a real number over complex. These were intuitive, not very surprising rules. The absolute value being multiplicative is not a very exciting statement over the real numbers. Here is what we're going to prove today. Given the properties we already developed about complex numbers, to have this statement true over the complex numbers, I squared equals -1 is a necessary condition. Okay, let's prove this statement. First, we're going to say let our mystery I squared be denoted by x plus yi, where x and y are real numbers. Every time you're looking for a complex number, really you're looking for two real numbers. And let us look at these two statements. Both of these statements deal with the absolute value being multiplicative, and both address a specific example. Let's see what we get from the first one. The absolute value of I is 1, right? I corresponds to the point 0, 1 on the coordinate system. That's 1 unit away from the origin. So 1 times 1 is the left-hand side. The right-hand side is the absolute value of I squared. That is, because we labeled I squared x plus yi, that is going to be square root of x squared plus y squared. This is an equation with real numbers. Once we square both sides, we obtain x squared plus y squared equals 1. The other statement is similar but restated on 1 plus I and 1 minus I. To determine the absolute value of 1 plus I, we identify a point corresponding to the complex number. That point is 1, 1. And then by the Pythagorean theorem, the hypotenuse of this isosceles right triangle turns out to be square root of 2. And similarly, this one is also square root of 2. Therefore, the left-hand side is square root of 2 times square root of 2. On the right-hand side, two terms cancel out each other, and we're left with 1 minus I squared. I squared is still x plus yi. And therefore, 1 minus I squared is a complex number with real part 1 minus x and imaginary part minus y times I. And when we take the absolute value of that, that is again by the Pythagorean theorem. So it's basically square root of 1 minus x squared plus negative y squared. Let us square both sides of the equation. So at this point, we have again arrived to an equation in real numbers, x and y. Our second equation is 3 equals x squared plus y squared minus 2x. Recall the first equation, which says that x squared plus y squared needs to be 1. We can just substitute 1 into x squared plus y squared. We get 3 equals 1 minus 2x. Solve for x. Get that x is -1. Remember, x and y are real numbers. If x is -1, minus 1 squared will not leave any space left for y, then 0. We got that x is -1 and y is 0, which means that I squared has to be -1.